Effectiveness of safety design features. The document guidance of implementation of the ASH to Strategic Highway Safety Plan, published by the Transportation Research Board, consists of several guides, each of which gives a set of objectives and strategies to improve safety at specific locations. So, Table 5.10 gives some of these objectives and strategies for a few locations. So, we have here different crash types, and each of it has the different objectives and strategies. So the first crash type is the collisions with trees in hazardous locations. Next is the head-on collisions, the unsignalized intersection collisions, collisions on horizontal curves, collisions involving pedestrians, and collisions at signalized intersections. So, summary of research results on safety effectiveness of highway design features. So, the FHWA has also published a series of reports that summarize the results of research dealing with safety effectiveness of highway design features. These reports provide useful information about the relationship between crashes and highway geometrics. These results generally support the strategies given in Table 5.10 for reducing crashes at specific locations. Among the features to be considered in this chapter are access control, alignment, cross sections, intersections, and pedestrians and bicyclists. So, research results that spanned a 30-year period were examined, and in some instances, studies dating before 1973 were found to be the most definitive available. Design features are discussed in the following sections based on the information from these FHWA reports. Access control, defined as some combination of at-grade intersections, business and private driveways, and median crossovers. For any given highway, access control can range from full control, such as an interstate highway, to no access control, common on most urban highways. So, the reason why access control improves safety is because there are fewer unexpected events caused by vehicles entering and leaving the traffic stream at slower speeds, resulting in less interference with through traffic. The effect of control of access shows that the total crash rate per million vehicle miles is almost 3 times as great on roads in urban areas with no access control that on fully controlled highways. Alignment. The geometric design of highways involves three elements. First is the vertical alignment, second, the horizontal alignment, and third is the cross section. Design speed is the determining factor in the selection of the alignment needed for the motorist to have sufficient sight distance to safely stop or reduce speed as required by changing traffic and environmental conditions. A safe design ensures that traffic can flow at a uniform speed while traveling in a road that changes in a horizontal or vertical direction. So, the design of the vertical alignment, which includes tangent grades and sag or crest vertical curves, is influenced by consideration of terrain, cost, and safety. Generally, crash rates for downgrades are higher than for upgrades. One study reported that only 34.6% of crashes occurred on level grade, whereas 65.4% occurred on a grade or at the location where grades change. So the design of the horizontal alignment, which consists of level tangents connected by circular curves, is influenced by design speed and super elevation of the curve itself. So crash rates for horizontal curves are higher than on tangent sections, which rates ranging between 1.5 and 4 times greater than on street sections. So several factors appear to influence the safety importance of horizontal curves, including the traffic volume and mix, geometric features of the curve, cross-section, roadside hazards, stopping sight distance, vertical alignment, superimposed on horizontal alignment, distance between curves and between the nearest intersection or bridge, pavement friction, and the traffic control devices. So the improvement of horizontal curve design involves 3 steps. First is problem sites must be identified based on crash history and roadway conditions. Second, improvements should be evaluated and implemented. Third, before and after studies of crash performance should be conducted to assess the effectiveness of the changes. So, cross sections. One of the most important roadway features affecting safety is the highway cross section. So, the road may be constructed on on an embankment or field section or depressed below the natural grade. Cross-section elements including through and passing lanes, medians, and left turn lanes may be added when a two-lane road is inadequate, possibly improving both traffic operations and safety. So safety improvements in the highway cross-section are usually focused on two-lane roads with the exception of clear zone treatments and median design for multi-lane highways. So we have here the table 5.13, which is the effect of lane widening for related crash types on two-lane rural roads. And we also have here the 5.14, the effect of shoulder widening for related crash types on two-lane rural roads. So we have an example, the crash prevention from lane and shoulder widening. So records indicate that there have been a total of 53 crashes per year over a 3-year period along a two-lane rural roadway section with 10-foot lanes and 2-foot unpaved shoulders. The highway is located in a mountainous area where average daily traffic is 4,000 vehicles per day. Determine the crash prevention that can be expected if only the lanes are widened to 12 foot, if only the shoulders are paved and widened to 6 foot, and if both measures are implemented together. So we have here, first is to compute the number of cross sections related crashes prevented using factors in table 5.16. So A is the crash prevented due to lane widening alone. So in table 5.13, the reduction is 23%. So we have the crashes prevented is equal to 32 times 0.23 is equal to 7 crashes prevented per year. And B, crash prevented due to shoulder widening and paving alone. So from table 5.14, the reduction is 29%. So the crash prevented is equal to 32 times 0.29 is equal to 9 crashes prevented per year. And in letter C, crash prevention due to both lane and shoulder widening, we have the reduction is 46%. So the crash prevented is equal to 32 times 0.46 is equal to 15 crashes prevented per year. So among the means to increase the roadside recovery distance are relocating utility poles, removing trees, flattening side slopes to maximum 4:1 ratio, and removing other obstacles such as bridge abutments, fences, mailboxes, and guardrails. So, when highway signs or obstacles such as mailboxes cannot be relocated, they should be mounted so as to break away when struck by a moving vehicle, thus minimizing crash severity. So, when two-lane roads become more heavily traveled, particularly in suburban, commercial, and recreational areas, crash rates tend to increase. The reasons were discussed earlier and include lack of passing opportunities, increased numbers of access points, mixed traffic including trucks and cars, in local and third destinations. Without the opportunity to create a multi-lane facility, there are several alternative operational and safety treatments possible. So these are: first is the passing lanes, and the second is the short four lanes sections. Third is the use of paved shoulders. Fourth is torn out lanes for slower moving traffic, especially on upgrades. And lastly, the two-way left turn lanes. So these options were evaluated for 138 treated sites, and crash data were compared with standard two-lane sections. So the results of these are valid for high volume conditions. For the option used of paved shoulders, no effect was noted, whereas for the other options, reduction in fatal and injury crashes range from 30 to 85%. Since the results are site specific, the operational treatment selected may not always be appropriate, and specific site studies are required. Intersections. Intersections represent the site of most urban vehicle crashes in the United States. The number of crashes at intersections has increased by 14% over a 20-year period. This result is not surprising since intersections are the confluence of many vehicle and pedestrian paths that may conflict with each other. An encouraging trend, however, is the reduction in severity of intersection crashes, such that fatal crashes have reduced by 11% over the same 20-year period to 28% of the total. The reduction in fatalities is the result of improvements in intersection design, use of passenger restraints, separation of vehicles from pedestrians, enhanced visibility, and improvements in traffic control devices. So, in urban areas with high traffic volumes, intersections must accommodate a high volume of turning movements that tran- traverse a large surface area. In this situation, channelization is an effective means to improve safety. So right turn only lanes have become recognized as a simple means to separate through traffic from slow turning traffic. For left turning traffic, however, several options are available, including left turn storage lanes and raised dividers to guide traffic through the intersection area. So, types of lane dividers used to intersection channelization are raised reflectors, painted lines, barriers, and medians. Crash rates also are affected by the sight distance available to motorists as they approach an intersection. Stopping sight distance is effective by horizontal and vertical alignment, vertical curve lengths, and horizontal curve radii should be selected to conform with design speeds. When this is not feasible, advisory speed limit signs should be posted. The ability to see traffic that approaches from a cross street is dependent on obtaining a clear diagonal line of sight. When blocked by foliage, buildings, or other obstructions, the sight line may be insufficient to permit a vehicle from stopping in time to avoid colliding with side street traffic. So, the following example illustrates in general terms the effect of sight distance on safety. However, in this design of an intersection, in order to account for adequate sight distance, the approach velocity must be taken into account. So, we have here the figure 5.8, increased sight radius by removal of obstacles. So we have here the before and after. So in table 5.19, we have the crash reduction per year due to increased intersection sight distance. So example 5.11, calculating the crash reduction due to increased sight radius. So a motorist is 50 foot from an intersection and sees a vehicle approaching from the right when it is 20 foot from the intersection. After removal of the foliage that has been blocking on the sight lane, it is now possible to see the same vehicle when it is 75 foot from the intersection. Average daily traffic volumes on the main roadway are 12,000 vehicles per day. Prior to removal of the obstructing foliage, the average number of crashes per year was 8.6. Determine the expected number of crashes per year after the foliage has been removed based on the research data provided in table 5.19. So from table 5.19, the crash reduction is 2.26 crashes per year, and the average number of crashes per year is equal to 8.60 minus 2.26, so we have a total of 6.34 crashes per year. So, pedestrian facilities. The safety of pedestrians is of great concern to traffic and highway engineers. Efforts to reduce pedestrian and bicycle crashes involve education, enforcement, and engineering measures, as is the case for motor vehicle crashes. In addition, the characteristics of pedestrian crashes indicate that factors related to occurrence include age, sex, alcohol use, time of day, urban or rural area type, end intersection or mid-block cross location. So, the common types of pedestrian crashes are the dart out, intersection dash, multiple threat, vehicle turn or merge, bus stop, the walking along roadway. That's all. And next is the neighborhood traffic control measures. So we have these semi diverters, the chokers or narrowing, the diagonal diverters, and cul-de-sac or street closures. So safety is an important consideration in the design operation of streets and highways. Traffic and highway engineers working with enforcement officials are constantly seeking better ways to ensure safety for the motorists and pedestrians. So, a highway safety improvement process is in place, which involves planning, implementation, and evaluation. The planning process requires that engineers collect and maintain traffic safety data, identify hazardous locations, conduct engineering studies, and establish project priorities. Some methods for analyzing crash data are presented. It should be noted that some of these methods have flaws that were discussed, and the analyst has to be cautious in making definitive conclusions based on the results obtained from the use of them.